Okay, well, I'm going to get started.
Are you going to introduce yourself?
I'm going to introduce myself. My name's Heidi Fearn. I'm from Cal State University, Fullerton. I've been there for, since 1991. So I've been teaching for like 27 years.
Wow.
Anyway, this is going to be very brief. I'm not going to take too much time. I want to tell you about the updates that we've been doing very, very recently at Fullerton, namely the last 2 weeks before coming here, essentially. So here again is the Mega Drive. There it is. Actually, there it is. And here it is in parts. And you may know that Jim has been making new stacks. So we've got a whole bunch of new PZT SM111, and he's been building these stacks like crazy. Not the ones with a hole in. I just had this one available to show you. Well, basically, this is how he does all the stacks. He uses this little thing with a little plastic, and then you put down a PZT ring, you put down an electrode, and you put glue in between, obviously, and all the electrodes are sanded both sides, and then you put all the epoxy stuff on there. Something about the epoxy, by the way. It turns out that Jim had been using an old method of curing the epoxy. He was told by an expert in the field that you're supposed to let it sit for a little while and then stick it in an oven and heat it at 160 Fahrenheit for 2 hours. Now that appears to have changed over the years. So recently we looked up the specs for the epoxy agent, and in our says you're supposed to leave it at room temperature for 24 hours, and then cure it at 2 hours for 212 degrees Fahrenheit. So that's nearly 100 degrees C. So we were way off the curing the actual temperature. So that means that every time that we had build a stack, it always seemed to have slightly different properties. And so what we need to do is we want these things to build arrays with, so we want them to have very similar properties. So the deal is we need something better than a 30-year-old toaster oven like this thing. And, and the little temperature gauge here, you probably see, actually I'll just use the manual stick here. You see this little thermometer we've got inside the oven, because this dial, the first mark on it is actually at 250 degrees Fahrenheit. So the other marks you see are the on-off switch, and then Jim has actually made some marks in pen on here to try and guesstimate where the 160 mark was. And that's not a good thing. I mean, really, I can see Martin shaking his head. And you're right, we need something a little bit better than that, okay? So what we're going to do now, this is I'll tell you what I'm going to do in a minute, but this is one of the vector network analysis scans that we did when we're doing the 2 hours at 160F. And you notice that in this particular stack called Nu5, there's really nothing going on here. And this is normally where we see a bit of a resonance dip, and that would give us the resonance at 36 kilohertz. But there was nothing here, so this one really didn't show much of anything. So we thought, well, why not we try to reheat this thing and see if we can get it to do so. So we thought the curing of the epoxy was the problem. And so I reheated it at Jose's advice for 4 hours at that same temperature, 160 degrees Fahrenheit. And we look now we've got this little bit of a blip going on at 32.4-ish kilohertz. And that's actually going to give us we don't actually run at the resonance, we run slightly higher. So that's actually going to give us a thrust at around about 36.3 kilohertz, which is very similar to the demo device that we sent to you guys. So although you were running it at the resonance, since we have the old amplifier, which is a carve-in audio amplifier, only 2 ohms kind of resistance or impedance, we have to use a step-up transformer, and then that gives us the actual resonance at 36.3 kilohertz. Okay, so I'm looking for this little blip here, and that's what's going to give us the right frequency that we want. Yes?
Okay, you said 160 degrees Fahrenheit.
Yes.
That is 71 degrees centigrade.
Yes, I was just being a little careless. So yes, 71 degrees centigrade.
But as I understand, TU Dresden actually cured their samples at 67 degrees centigrade, so it's even lower than that?
It's even lower. TISC. Yeah, we actually looked up, it's probably at Jim's advice, we actually looked up for that specific resonance, the resin that we bought, and apparently the actual curing is 24 hours at room temperature, and then you're supposed to go 2 hours at 212 Fahrenheit, or about 100 degrees C. So, yes, he used a different epoxy. So he was using something that was grey coloured. Ours is clear. So they had a different epoxy, and they probably used the correct curing time.
What epoxy are you using?
Silver epoxy.
What is the technical work? Okay, I'll discuss it later on.
I'll send you the data.
Do you know what the TG is?
What?
The glass transition temperature.
Not from memory, but we'll send you the data sheet.
But anyway, it is nothing changed through the years. That EPON system has had the cure temperature of 100 degrees C. The issue is again that whether you want to have the optimal cure for the epoxy such that it has the highest glass transition temperature, or you want to take into account the fact that it will contract as you go from the glass transition temperature to room temperature and will produce residual stresses if it is glued, for example, to this PCT. So the higher the temperature at which you cure it, the higher the residual stresses are going to be. So as you go to higher temperature, you're going to have a material that has higher temperature resistance, but on the other hand, you're going to have more residual stresses, which means that the material is going to be more prone to cracking because it's going to be closer to the threshold at which you crack. Therefore, the question of an optimal cure is not something you can get from...
Right, not necessarily going straight to the manufacturer's recommended setting. Maybe we have to do a little bit of testing and decide, maybe we start at 70, then go up to 80 degrees C, and then 90 degrees, and then the recommended 100 degrees C, and we figure out which one of those is the best for what we want to do. Okay? Yes?
So you're looking for a dip in the impedance, which would indicate some kind of resonance?
Yes. And normally around here, we're looking here.
The 36 kilohertz resonance that you're talking about is not in this diagram because you're measuring the impedance of the thruster above without the amplifier and the separate transformer.
It's probably one of these little wiggles here, but what we're looking for something going on in this region right here.
Yeah, but it's not clearly there.
No, not. I didn't write in exactly which one it was.
If you're emphasizing the propagation resonance as 36 kilohertz, that is present in your system, that I would suggest measuring the current and the voltage with the amplifier and the separate transformer connected to the thruster, and then do a frequency sweep.
Right.
You can get the impedance curve from your voltage and
right.
measurements. Then you would be able to show maybe a significant dip in the impedance at that frequency.
Right. No, it's good advice, and I'll take every advice I can get. So thank you. So here's a reheat at 80, and we didn't see really any change from the reheat after 4 hours at 70. It really didn't do anything new after that. And again, I reheated it at 100 degrees C. Again, really nothing is really changing after that 4 hour at 70 degrees C. This is all looking pretty much the same. Maybe a little shift here, but very little happened. So what we really want to do is start with virgin stacks, ones that haven't been cured yet, and then do a similar test to that. Do it 70, do it 80, 90, and then maybe do the measurements of the current and voltage, like you said, and really see what's going on there and which is going to be the best situation for us. So here's what we bought. So rather than that nasty little toaster oven, which is 30 years old, which is going in the trash, by the way, we're going to get this guy, which has an accuracy of 0.1 degrees C and very, very stable inside. So I don't have to worry about where exactly I place the device inside the oven. It should all have exactly the same temperature, a very, very good temperature anyway. And then we're going to do the testing using this. And that's, of course, the NIAC grant has enabled us to buy this because it's a rather expensive piece of lab equipment. We just made use of the $30 toaster oven until now. So that's what we're going to get. So lose the toaster oven. Now, we've done a whole bunch of tests. After you guys in the Germany did your civil paper mentioning certain things, they did pressure tests and magnetic tests and tests by taking the device and rotating it inside the box rather than just rotating the entire box. We decided to do the same exact tests ourselves to see what would happen. So we've got magnetic tests, pressure tests, reverse the device in the box rather than just turn the whole box around and see what that does. So I'm going to show you all that lot. And also I just wanted to get the natural period of the pendulum as well. And that day I couldn't do any testing because guess what? There was an earthquake, California. Yeah, there was an earthquake, and we're on the 5th floor. So you can imagine, in a building that's designed to shake, I wasn't going to be taking any data that day. So I took out the magnets. So there was no magnets in the machine at this time, and you can basically see the graph going, and that was the earthquake, 2.6, which you wouldn't even feel, but this device can obviously pick that up pretty easily. And I took the data from that and using the picoscope, and I put it into Mathematica and did a curve fit. I'll show you how to do a curve fine fit deal. And the blue line is what I got from Mathematica, and the red one is the actual curve. So you see it fits pretty well, and I got the period to be, so the natural period is 5.7-ish seconds for the pendulum. That's without the magnets in there. So I want to do the same thing with the magnets, but again, I was stressed for time, so I wanted to put the device in and try to do two devices at once, not just one device. So instead of doing leaving the magnets out, putting the magnets back in and then doing another test, I went ahead and started playing with something else. That often happens, you know, I get sidetracked and I do something different. So, oh, and this is another thing. So in amongst the many things I'm trying to do, I'm trying to upgrade our old system here. The system that you see on the left is the old system, and on the right you see the new system. So all these three boxes here are basically represent our frequency generation system, and now we're going to have the Rigol generator here is going to be doing all our frequency generation. It can do arbitrary waveforms. It's got like 160 odd different waveforms built in. It can do linear sweeps. It can do logarithmic sweeps. It can do ramps. It can sing and dance and probably make coffee too. And at the price we paid for it, it should do as well. And so I've got this all programmed to do all the kinds of sweeps that Jim normally does. You know, there's like the pulse thing, and then the sweep, linear sweep, and then the other pulse. So that's all set up, ready to go in lab view. And also a pulse and a pulse, which I can also do sweep if I want to, with a duration in between the pulses to let it cool off a little bit. And I'm working on the chirp, only I'm finding that the Rigol says it can handle a really big arbitrary waveform. It lies. It can handle a really big arbitrary waveform in volatile memory. When I try to put it in the actual memory on the device itself, the internal memory, it's telling me that my file is too big, basically. So I put it in, it seems to store, and I try to recall it and run it, and I get a flat waveform. So I'm having a little issue there, and maybe I could, if there's any experts in the audience on LabVIEW, because I'm a total novice at that, I wouldn't mind sending you files and having you guys help me out. But I'll figure it out eventually, but I've got a few things I've got to do, so that's on the back burner for now. Now, what I wanted to try, and I was desperate to try, is the Duo drive, right? So these two drives, this is one I just recently tested, new 4, and this is the old demo device that was sent to Dresden, okay? And it's all nice and new and shiny and working again with new wires and some stuff on there. And this little thing here is a 3/4 inch tube, and this is a threaded rod. It's an 832 threaded rod, and basically every single side of the cube has got a hole, and with a threaded hole. So the two sides, we're going to take out the Faraday cage and then slot this threaded tube into the C-shaped holder for the yoke on the balance beam. And then these things, we can either have them horizontal or vertical inside the chamber. So that's what it looks like inside a chamber. Here it's in the vertical configuration, and here you see the yoke where we just took out the Faraday cage, which is sort of sitting down here in the vacuum. I slid that thing in instead. Now you may notice that there's no box around the thing, because the box is too small, it doesn't fit. So the first test I did without using a surrounding box. And also, you see all these wires dangling around here? I can only hook in the two thermistors in parallel, so the accelerometers or strain gauges are hooked up in parallel, so they're both going to one little pin, and the power cords also are hooked up to one in parallel, hooked up to one pin. But I had to put extensions on, so the leads are a lot longer than they normally are. Okay, so that's what it looks like in the chamber, and let me show you the sort of results we were getting. So we were getting the usual sort of, transient. They're really just transients because the pulses are so small. They're only like 3-second pulses, and then a sweep and another 3-second pulse. But you're seeing definite transients here, and then another one as it sweeps through the resonance, and then a switch-off transient at the end. But notice also this weird shift. It shifted from here to up here somewhere, and it's slowly kind of going down. And that, to me, this kind of shift is a thermal imprint. So there's a definite thermal buoyancy, something going on there, which I didn't normally see when the thing was inside the box. So yes.
That's for a fixed frequency?
That is for 36.3 kilohertz, exactly the same as we use for the demo device. So this new 4 just happened to have the same exact resonance frequency.
Pulse, power on, off.
Power. This is the power on. Then there's a sweep, which is a sweep through about 24 kilohertz. So it starts high, sweeps through the resonance and then goes low. And then here's another pulse, which is at 36, which again, a little 3-second little pulse there. So all you're really seeing there are the transients. And then you see here, the forward thrust, and here it is when it's reversed. What I did was just rotate the whole thing over, so the wires rotate as well, and then that's why you're seeing this whole thing is upside down now, right? So, but you're seeing this it sort of peaks and then it seems to slowly go down back to the zero line there, and that is definitely thermal. So I was wondering, well, am I heating up the device so much that it's doing that, or why is that the case? So I took a look at the thermistor, which is in the cap of one of the devices. It was actually the demo device that you guys had in Dresden, and this is what I saw from the aluminum cap thermistor. You see this temperature here? It starts at around 23, right? So just kind of metal temperature, room temperature, and then it only rose to just over 24, so a very small change during that whole sequence, the pulse, sweep, pulse, very small change in temperature, and then of course you get this gradual come back down. So that's what was happening to the demo device during that run, really, really small change in temperature. But you saw that huge thermal drift, so where the heck was that coming from? We think it was coming from the wires. Because the whole thing was outside the box. It was the wires getting hot. And then if we see a thermal drift when inside the Faraday cage, it must be because the wires are actually heating the device. And the actual Faraday cage feels warm when you touch it. So it's because this was out in the open with no box around it that the actual temperature of the device seems to be really small. Because remember, we're not on resonance. We're slightly off the resonance. So it's not going to get that hot. And as you can see there, really the caps didn't get that hot. Of course, the stack itself, the thermistor isn't embedded in the stack, so the stack may be getting a little bit hotter than that. But what we were seeing is actually really low in comparison to what we normally saw when the device was inside the Faraday cage, because then those wires are heating up the whole box, and then it's actually making the stack hotter. So we were thinking this is actually a nice sign that if I maybe shrink down the wires a little bit, I won't get the thermal signature that I saw before. So that's one thing I've got to do. I've got to go back and this is what you get from a single drive, forward minus reverse. You see, you really don't get that huge thermal signature anymore. It's that. So we think this is when it's inside the box, the Faraday cage. So we think that the heating was actually coming from the wires in the system. So that's average forward minus reverse, and I'm averaging about 6 runs forward and 6 runs reversed. That's all to get that. So this is when it's inside the Faraday cage, just one device inside the Faraday cage. And this is the old device, the demo device that we sent to Dresden. So you do see we are seeing the thrust here, and there is a little bit of a steady thrust going on here. But just look at the transient. If I just look at the transient, I'm going from what, 0.4 down to minus 0.4, so about 0.8, 0.9, let's say 0.8. 0.8. Let me go back one. Go back 2, and here you see the thrust thing the scale has actually changed somewhat. So now I'm going from let's say from here, what's that, 0.2, well actually that's 2, so maybe 3, so maybe I've got 3-4 micronewtons. So it's about times 2-ish. So from 0.8 to about 2 to 3, actually it's maybe slightly even more, but I'm not going to say more than that, but I'm just going to say it's at least double, right, with the 2. Yes?
Why are you ruling out the possibility that there's not some other part of the thruster that's heating up and that's not properly transmitted to the aluminum?
It could be. I've got to test that. But it's just weird that I'm seeing this huge thermal thing when it's outside the box, and when it's inside the box, the temperature of the aluminum cap is much higher. It goes up at least 10 degrees, and when it's outside the box, the temperature of the aluminum cap was only 2 or 3 degrees. So I'm wondering what can do that. The wires are much longer now when it's outside of the box. So I thought the first thing I thought of was the wires, because they're longer. But maybe there could be something else. That's the thing I have to test when I get back. I honestly don't know at this point. So I'm going to.
Hold a lot of current. And if
they can.
Current in the thruster that's heating the thruster, then there's no current in the cables as well. So
yeah, well, I'm just not sure what else it can be. It could be the brass, maybe the brass masses, or maybe the brass masses are absorbing some of that heat, because now I've got the same voltage going to 2 drives, and the brass seems to slowly heat up and then slowly decay again, where the aluminum heats up more rapidly. So I'm not sure.
Check how many pounds resistance there is in the contacts that the wires are making with the outside.
Right.
It's very easy to get dirty contacts.
Yeah, and of course now there are more contacts because I had to put an extension on the wire, so the little contact clips, they may be heating up possibly. So I'm going to have to check that. So there's a few things I can check. Yes?
Monitor current
We are not monitoring current right now, but we're going to. In fact, we do have the ability to do that. It's just that I was in a kind of a hurry doing this, so I didn't put in another cable to do that, but we can do that.
How are you planning to monitor current in the future?
I'm sorry?
How are you planning to in the future? You say
Oh, we have when the voltage comes out of the transformer, there is a little box that has the electronics in, and I've got voltage that I've been monitoring, and there's also a current output. So I can see the current that's going to the device. You want me to measure the current actually across the device, or the current going to the device?
Through the device.
Through the device. Well, this is the current on the way to the device. Do you want me to measure it when it goes through? So I'm measuring on the wrong side. I can do that. We can fix that. So again, there's several things I've got to do. So on my to-do list. Okay. So this is basically what we saw with the duo drive. I just want to point out now we are seeing a lot more thrust in the transients anyway than we were before. But I have this weird thermal problem that I've got to figure out. Again, there was the heating. That's one drive. And this is the duo drive, again, the two drives, forward minus reverse thrust. Again, it seems to cancel this thing a little bit, but not that much, so there's still a thermal thing going on here we've got to fix.
Have you tested your new drive alone?
Yes. Yes, same thing exactly as the demo device.
Oh, yeah.
Yeah, so what I've been doing, Jim has made about 12 different devices now, and I've been systematically going through every device, putting it on the balance, doing a VNA before, doing the testing, forward, reverse, forward minus reverse, forward plus reverse, and then trying to find out what the resonance frequency is, and trying to find two or more that have the same resonance frequency, so we could try using an array of them. So far I've only got two that are at 36.3. I'm looking for more, and I've still got work to do there. So this is what I've been doing just prior to this conference. I wanted to get 4 up and running, but we only had the 2 that were the same frequency, and we've only got one way of getting the voltage to there. So it's basically the voltage is in parallel now, but going to both. Let's see, that's forward plus reverse. So any non-reversing signal should show up here, and you're really not seeing a whole lot of anything, so I think that's just noise. So yeah, there's really nothing going on there. Things to do, well, obviously I need to do a lot more of the console analysis, and obviously also of the beam. So it was on my to-do list. I've got a very long to-do list, so that's something I've got to do, a finite element analysis of the entire beam structure. This is some console stuff, so I do have access to console, but only a couple of modules. So I may have to spend a bit more money getting another module or two. But this is another little thing we were doing, little 5mm by 5mm square stack, which is just commercial off the shelf. We were testing that as well. So anyway, there's more console testing to do. I definitely want to do a finite element analysis of the entire beam, and maybe Jose can help me out doing something analytically as well. So that's something else I've got to do. Oh, to the tests. So pressure test, magnetic test, testing of reversing the device inside the box rather than reversing the entire box. Those are coming up now. Let me just use the big stick here.
What do you mean with pressure test?
I will tell you. So the ones that you were seeing before, the runs that I showed you, they're all below 30 millitorr. In fact, they're normally around 5 millitorr or so. That's usually what pressure I have the chamber at. These ones, I let the pressure go up to way above that, above 30. I think 30 millitorr is the kind of threshold, and below that everything's fine. Above 30 millitorr, you sometimes get spurious kind of things, more buoyancy shows up. So I thought I'd run it at 80 millitorr just to see if something else happened that I want, any weird effects that might show up. So this is what I saw, and this was running at 80 millitorr. So this again is just one device, the demo device I sent to Dresden. So maybe there's a bit of thermal drift going on here, but there's the on spike, there's a bit of thrust going on here, and there's the off. So again, the usual transients and the steady thrust. That's forward. Yeah, I'm thinking there may be a bit of thermal stuff in there too. So this is what it looks like when you run above 80 millitorr. So I wouldn't trust these at all. I wouldn't trust these. And here again is the reverse. Again, you notice the transients go the opposite way, as you might expect. This is forward minus reverse. And here it looks actually fairly level. So I was surprised I was getting a nice cancellation of that and getting a fairly straight zero line. And then this is a forward plus reverse. So you really don't see any non-reversing thrusts in there. So I think this is a good thing. And this is something I suggested Jamie do too, forward minus reverse, and see if he gets that nice straight line. He thought he was going to, but he hadn't actually done it. So that's something that he needs to do as well. So it wasn't so terrible, although as Ray said, these do look a little bit bigger, and so I think it's not real thrust, I think it's buoyancy or something like that going on. So that was the pressure test.
But TU Dresden showed a number of cases that had an X, right? So these tests some of those X cases?
I would never do a test with a pressure above 30 millitorr. All the tests that were done for the V to the fourth thing were done well below 30 millitorr. This is 80 millitorr. So I wanted to see if we got something weird happening if I used a higher pressure in the chamber.
Very similar.
Oh, they are very similar. So it actually doesn't seem to matter too much if I use a higher pressure. But only that these things are a little bit higher than before, and I think that's an artifact.
No, but
So,
my question has to do with the presentation from TU Dresden. It
Yes.
showed reversing a number of things.
yes,
And some of the things they had a check mark, whether it was according to expectations
Right.
or an X.
right.
It was,
And these are exactly as I'd expect. So forward is going, notice that when it's forward, you have it goes down, and it stays down a little bit, and then it goes up. When you reverse, it goes up, stays up, and then it goes down. So it reverses exactly.
I'm sorry, I don't think that you are following what I'm saying.
Maybe not.
If you remember that the presentation that they had a number of cases where they were doing certain things.
Yeah, they were going forward, they were going
It
reverse.
has nothing to do with a case whether you have a transit or not. I'm talking doing this rotation, that rotation, this, that, right?
Okay.
Certain things had a check mark, other ones did not. What I'm asking you is, it looks like you're not doing the full set that.
I didn't put it at 90 degrees, if that's what you mean, or I'll have the thing going vertically or something like that.
This pressure test has nothing to do with our tests. We always run at very, well, at 0.
Yeah, 2 to the power of -2 millibar.
Okay.
Yeah.
Okay. So I can move on to a different test
high
then.
pressure or not.
Right. So I was just testing for high pressure weirdness.
Forget about the pressure. Okay? Forget about the pressure. I'm just talking about the methodology of the experiments.
The one that we're using here is 90 degrees.
Exactly. So what is missing here? The 90 degrees.
So basically I take the device and rather than going forward or backwards, it's going upwards.
Sorry.
And I shouldn't get anything.
Please. I'm addressing the methodology of the test.
Okay, so you want me to do another test? I'll do it. I will do it.
Well, I don't want you to do anything. I just said, well, don't you think that to address what presented, don't you think it's important to, because it was the 90 degree, did it have an X?
For some measurements, yes. For some measurements, it was
Okay,
okay.
so
Right.
don't you think that in order to address the
Yes.
fairness of TU Dresden to see whether you have the same thing or not,
Right.
you should follow
This is the first time I've seen their test, so I didn't know what the test they were doing. So now I know that they're doing the vertical one as well. I can do that. Jim has done that in the past and seen nothing.
No, but I want to see the things to do. Because
Right, sure. I'll put that on the list.
It's not exactly vertical, it's just parallel to the axis of
Okay, parallel to the axis of the beam. I can do that.
Dummy resistant load is
And we've also done that too, and Jim has seen nothing. So those things, yes, dummy load. I heard that. So
can you
we can definitely on the list. It's on the list. I'm going to get a really long list, but things to do. I'll be busy for a while. It's a good thing. Oh yeah, Mike.
So in every test, there's this sharp transient behavior of the on and off.
Yes.
Can you talk a little bit about what you attribute the transient to? And
I will.
specifically, I mean, is it clear whether that's due to the inrush of current with the power on, or is
It's
it due
the
to
rate of change of
beginning-
power. That's
Sure.
it.
Or is it due to the beginning of vibration of the?
We think it's rate of change of power to the device because this is power on, so the power level is increasing, so it goes one way, and this is power off, so the rate of change of power is decreasing, so it goes the other way. So increase, decrease, they flip direction. That's what we think it is.
So is that some part of your theory then of the?
Yes. In fact, when we have a DC supply, we don't see thrust, but if I switch on and off, you'll see a tiny little transient. And not a very good one, because you really need to have it on resonance as well, like we're doing here with the AC current. But you will see a very, very small, if you know what you're looking for, really, really small transient, even when you just switch something on and switch something off. It's even a DC power.
So if you turn on the same type of power sourcing to just a little resistor, or you still have a, inrush of current and everything, what happens in that case?
Well, again, when I saw a little transient in the DC supply case, I must have done like 150 runs averaged to actually see it. In one run, you wouldn't see anything.
I don't know what the DC supply case is. I'm just asking whenever this power is.
Last night, that was
Yeah, Jim showed it last night. I did 150 runs just using a DC at about 150 volts. That's about as much as I could find in a power supply at Fullerton. And I switched it on and I switched it off. And I saw I was looking for something, what would happen if I just switched something on and off without having the AC resonant frequency present. Yes, Jim?
The way to test what Mike's talking about is to take just a regular capacitor with 19 nanofarads, where you're not expecting the Mach effect. Replace the device with that, and then run it and see whether or not you get the switch.
You get a transient. Yeah, we've definitely. Jim has done that before. Yeah, I think it's all in his book. He's done the parallel to the beam, vertical beam. He's done all those things. He's also done the dummy capacitor thing before. But if you want me to do it again, I'll do it again. I don't mind. I'm good. It's been done, and we saw nothing. I saw nothing anyway, unless I did 150 runs and then averaged and you saw a tiny little transient. Because you really need to have the resonant frequency present. Yes, Jim?
Real quickly, the DC switching was done to see whether or not changing the center of mass of the device by turning it on at a steady voltage would produce any mechanical effect. And what she's saying is it's a very small switching transient, but no steady thrust. Okay, that's last night. The test you want is for us just to stick a routine run of capacitor in there in place of the device, and then run it that way and see whether or not the switching transients are a consequence of the electrical circuit, or they're a consequence of the power prediction in the non-effective equation. And we can do that. I'll be happy to do it for you.
Had that been done? She said that had
Yeah,
already
it's been done. It's been done, but not recently.
Okay.
So we'll just do it again, no problem. I'm going to flip through a couple of more slides, and then I'm only doing some tests, and then that's all I've got. So these are with a stack of neodymium magnets just outside the vacuum chamber. So this is with the magnets present. So I'm assuming that you remember what these things look like without the magnets present. It's very similar, only maybe now there's a little less thrust going on. So this dip isn't quite as big, the transients aren't quite as big. And what we think is happening is that the magnetic field is creating eddy currents in the beam itself. So it's sort of damping it out a little bit. It's not moving as far. So that kind of makes sense. So we're not seeing quite as much thrust as we did previously when the magnets were not present. So little eddy current business going on.
Eddy currents don't decrease the amplitude of the displacement, they just change damping.
The damping, yeah, but in our beam, it could maybe adjust it slightly, maybe a small deflection or slightly less. I don't know if you've ever seen something rolling down a hill, if you have two magnets and you have a little hill there, and you roll a disc of metal down, it kind of slows down when it gets to the magnets. That's what I'm saying. We're maybe slowing it down a little bit, and maybe we're not seeing quite as big a swing as you would normally. So I'm thinking the thrust may be the same, but the transients are a little bit smaller, so it's not swinging as much.
Could it be, you said your damping is almost at 1?
It's slightly less than 1.
If you go a little bit more damping, then
that's what I'm thinking. Yeah, I think that's what's going on. So basically, just a little bit less of a transient. I think the thrust levels are pretty much the same, but the transients are a bit smaller, and I think that's what's causing it, the eddy currents. And again, you can take forward minus reverse. Again, these things at the peaks here are a little bit smaller, and here it's pretty much straight through. Forward plus reverse, everything cancels out. There's no non-reversing thrust there. So that was the magnetic test. You've seen the pressure test. Now this is the reverse the device inside the Faraday cage without reversing the Faraday cage. Okay, that was something that you did as well inside your big box. So I'm doing it inside the little box. So this is the device reversed in the forward cage direction. So the cage is sitting like it would for the forward device, but I actually undid the cage, flipped the device around inside the box, and then ran it. So it's running in reverse mode right now. And this is what you see when you reverse the device in the forward cage. And this is what you see if you just take the device and just rotate the whole cage around. And I don't really see much difference between those two. They look exactly the same to me. And then, of course, I did the difference between those two, and you'd pretty much get noise. And that's our noise level right there. So I'm not seeing any difference between reversing the device inside the cage or just rotating the whole cage around. It makes no difference to us, because our box is really small, got small wires. I don't think it makes any difference. What else have I got here? Oh, I must have put the pressure test in twice, sorry about that. So as mentioned, this one is at 80 millitorn, it's the same thing I showed before. I was just playing with my slides on the side there, so didn't realize I'd already done that one, so I don't need to show that again. So more things to do, there are upgrades. We want a bigger chamber, preferably not plastic. I don't mind using a sapphire window to see what's going on, or even a little video camera inside, but I don't really want to go with plastic because it's the pumping out is a pain and it gets warm and I don't need it. So it would be much easier to use a metal cage as a metal vacuum chamber for a heat sink as well. So this thing is definitely not helping because it gets warm. I'd also want to try 4 devices, and I'm not sure. We could put 4 devices in here, but if we do any more than 4, we definitely need a bigger chamber because we're going to need a bigger everything. So that's something to do. Notice that Croc is still here. I've been trying to get rid of that thing, but he still seems to follow around the vacuum chamber wherever we go. And then the new one is on the way, and we've got. Yeah, I'll try that. Melt the thing. So again, thanks for coming to Estes Park. Here we are with the nice mountains in the background, and we got up early today, so I'm going to be drinking lots of coffee. So if I've been bouncing around too much, it's because I drank a lot of coffee this morning, just so you know. So thank you very much. That's it.